differential equations you can solve. The main one, and what we're studying in this section, is what's called a separable differential equation. Definition. A separable differential equation is any differential equation that can be written in the form dy over dx is equal to f of x times g of y. Now pay attention to this really quick and what this says. Now, in this class, this is always going to be the first derivative. I should note this does not have to be the first derivative. So it could be the nth derivative of y is equal to f of x times g of y. But more importantly here is the right side of this equation. Over here, this is a product of one function of only x's times one function of only y's. So we take a look at some examples of that, right? dy over dx is equal to x plus y is not separable because if we factor out an x, we get 1 plus y over x. Or if we factor out a y, we get x over y plus 1. And in either case, it cannot be written as a product of some function of x times some function of y. Whereas something like dy over dx equals, e to the y divided by x is 1 over x times e to the y is separable. Where here f of x equals 1 over x and g of y is equal to e to the y. And it could be, difficult to separate or rewrite that way. You might look at something and say, well, that's not separable. But e to the x times e to the y, if we use exponential rules, is separable. Okay, so there's an example of something that's not separable and some things that are separable. So why is something that's separable so dynamite? Well, how to solve separable differential equations. If it is separable, dy over dx equal to f of x times g of y, then what we're going to do is we're going to actually separate the variables. That is to say, we're going to multiply both sides by the differential dx. So we get dy is equal to f of x, g of y times dx. And then what we're going to do is we're going to divide both sides by g of y. So that we have 1 over g of y, whatever that is, I don't know, times dy is equal to f of x times dx. And so we have separated both variables on either side of the equal sign. So what do we mean by that? All y's and dy on the left, and all x's and dx on the right. Before we go any further, warning. If you take dy over dx equal to f of x gy, and you separate it the other way, this can also become 1 over f of x dx is equal to g of y divided by dy. This is also separated. This is also separated, but we want dx and dy in their respective numerators. And I'll tell you why. Because if we go back to this form here, which has dy and dx in their respective numerators, then we're going to use the old school equality that says whatever we do to one side of the equation, we can do to the other side of the equation. And in this particular case, we're going to integrate both sides. So once these are properly separated, we can integrate both sides. Now, whether or not you know how to integrate both sides, you're going to have to, it remains to be seen, and you're going to have to draw on your extensive knowledge of Calculus 2 over the past 8 weeks, right? But these should be simple things that you can integrate. It shouldn't be too crazy. And back to this warning. If we try to integrate both sides here, we never integrate with the differential in the denominator. We do not integrate with the dx or dy in the denominator. Ever. Don't do it, man. So that's the reason why you got to separate them correctly. Now, once you do that, and I don't know what this is going to be, but the idea is this is going to be some antiderivative. Let's call it capital G of y plus arbitrary constant 1 from integrating is going to be equal to some capital F of x plus arbitrary constant 2. And what we're going to be able to do is we're going to be able to subtract that constant 1 from both sides. G of y is equal to capital F of x plus C2 minus C1. And pay attention here. You're going to see a lot of this in the days to come. A lot of manipulation of these coefficients. Constant plus constant equals a constant. And since we don't know what they are, we can just say G of y is equal to capital F of x plus C3. And oftentimes what we do in our first course of differential equations is leave a paper trail letting us know, hey man, C3 is really equal to C2 minus C1. And then you can, if possible, solve for y, in which case I don't know how complicated capital G is, but if you had to, you could do the inverse operation, allowing you to solve for y. And then once we're done, if given what's called some initial condition, as we used to do in Calc 2 and Calc 1, if given some initial condition, like an XY ordered pair or y of x equals, or maybe I should say, f of a equals b, use the information to solve for C, the arbitrary constant. And we'll do all of that stuff in the examples to come. But that's the idea and that's the theory. If you can separate it, then you can integrate both sides and then hopefully solve for y. And that's one way to solve a differential equation. So in this day one, the only thing that we're doing is focusing on the mechanics. We're going to do some applications and some word problems on day two of this lecture.